it probably makes sense to do that before Thanksgiving. Could just do next Tuesday for that multiple choice. You've seen it before. The way you study for it is to understand what position, velocity, displacement, acceleration mean, and to know Newton's laws. There's no math involved. Any objection to, we could do it on the 21st also.
No.
Not the 21st? All right, you're good with the 19th?
Oh, I thought we can't do it on the 26th? What? Yeah, the 26th.
Problem with the 26th is everyone gonna be here? And everyone should be here, however, some people like to extend their vacations because they just love spending time with family. I think I'd rather do it the 19th.
Okay.
Yeah.
Can we do test corrections on that test?
Can you, no.
Oh.
All right, so let's,
Do we not have class after Thanksgiving break?
we do have class after Thanksgiving. I just wanted to get it out of the way before
I was
Thanksgiving.
just making sure.
What did you say? What's the study for?
It's basically chapters 2 through 5 in the textbook. The individual assignments are due on the 26th. That's the 11th through 14th stuff. Okay, was that what your question was?
Yeah.
Okay.
He said to divide what? I'll study for the day on
So we have that tonight?
No. I'm sorry.
Okay.
If you could do projectile motion experiments with,
Okay.
you know, just because Thanksgiving was really awkward once my parents split up, doesn't mean everybody's life is like that. So, sorry if it's a downer. This is approaching what I consider this is my least favorite time of year. So. Look of scared there.
And the grade for this class, when are we gonna see that?
Grades for this class?
Not today.
Well, I've handed stuff back, and I do have some, actually. Caroline, I have stuff for you, Riley. Viola? No? No?
When do we get the first exam back?
I've handed that back. You mean
But like
with the
after the
corrections?
break.
Yeah.
Oh, I don't know. Test corrections, I usually put that off till the very end. Yeah, that's it. Which quiz? Who is not taking the quiz yet? I've lost track. Everyone's taken the 8 through 10 quiz? Okay. That first one? In that first one where you're finding the centripetal force, and you're given mass, speed, and radius, there are two different formulas there, both involving MV and R. One is the formula for angular momentum of a particle, and the other one is for the centripetal force. So the L equals mvr, that's angular momentum. There's linear momentum right there, mv times r. Similar to torque is force times r. The other formula involving mv and r is mv squared over r, which is the one that's actually a force.
So is that the one I should have used with
Yes.
MD? Okay.
Yeah. The most common mistake I've seen on that is people picking the wrong formula. The most common major mistake, then there's the group of people who forget to square, hit a number in the calculator wrong. Think units are for other people, not them.
This one.
And, number 7?
Yeah.
Mistakenly astronauts orbit above gravity. All right, so that's finding G.
That one.
I have 2 formulas for force due to gravity. One formula for force due to gravity is mg, and the other one is, so that's mass of object. And the other one is used in generalized form, big G, mass of object, mass of planet, well, I guess Earth specifically in that case, over the distance squared. So it's asking you to find little g here, acceleration due to gravity. So the mass of the object is irrelevant. And we're left with this. G is a constant, 6.67, et cetera, times 10 to the negative 11th. Mass of the Earth, 5.98 times 10 to the 24th kilograms. Although on there I might have said 6 times 10 to the 24th. It did it someplace. And then R, well, R is center to center distance, and you're in orbit at, was it 100 kilometers up? 200, 150?
190 kilograms.
190 kilometers. So the distance, R, is from the center of the Earth to where that is, so it is going to be the radius of the Earth, 6.38 or 6.4, whichever one you're using, 6.38 times 10 to the 6th meters, plus 190 times 10 to the 3rd meters. That's the radius of the Earth plus how far you are above the surface of the Earth, squared. And so the denominator is really not much bigger than it was before, than at the surface of the Earth, so it's not a big change, so you end up being at, see, 9.8 at the surface of the Earth, and this puts you at somewhere around 9.2. I'm going off of memory here on that one.
Okay.
All right, other questions? Then let's talk about chapter 19. We might do this without Johanny, but if she comes back in time, she will participate in the way. All right, so we're talking about waves now. There are certain vocab words. Yay, vocab. Waves have certain characteristics that we will be using. One of the characteristics is period. Period is symbolized typically by a capital T, because period is a time. So it is the time to produce one cycle of repetitive motion. Earth goes around the sun. It seems to have at least done that for the last 60 years. The period is 1 year. It's how long it takes repetitive motion. It's how long it takes in order to do it once. The moon going around the Earth, its period is about 28 days, 27 point something. So anything with periodic motion, with regular repetitive motion, the period is how long it takes for whatever it's doing to do it once. Units, because everyone loves units. I will assume, since I'm not looking at you, all of you are nodding in agreement. The SI unit for period? Well, you tell me. Considering it's the time for something to happen.
Seconds.
Yep. Frequency. The symbol for frequency is the same symbol I used for friction, sort of a Baroque F. And similar to normal English, it's how often something occurs. Now, typically, you will see it in terms of cycles per second, the SI unit for frequency is the cycle per second. So period is a second per cycle, frequency is cycles per second. Matter of fact, not only are the units the flip of each other, the quantities are also. We have period is 1 over the frequency. Wavelength. The symbol is a lambda. Lowercase lambda. It's how far a wave travels in one period. So if you're doing battle ropes and you're swinging those ropes up and down like that, you get these waves that are propagating that are being sent down the rope, and the time it takes your hand to go up, down, and then back to where it started would be one period. How far that pulse went would be the wavelength. The units, SI units of wavelength, well, someone's going to tell me. What are the SI units of wavelength? There were several clues up there. Say it again?
Meters.
Yeah, meters. It's a length. It's how far something moves. Yeah, the SI. Amplitude. I don't know why I'm capitalizing it, but I just did an amplitude. Now the symbol for amplitude really is problem specific. If I'm just doing a generic amplitude, I'll just use a capital A. And I'm going to use the term distance, although really not the best term for that, because it is problem specific. An amplitude for how loud sound is would have a different unit than the amplitude for, what the pulses you're sending on a battle rope. So distance from the middle to the peak, or / trough. So if I'm sending these waves up and down along a rope, what you would see if you were standing on the side it would look something like that. The amplitude would be that distance right there. The wavelength would be that distance right there, or that distance to there, from any point on the wave to where it starts to repeat itself. All right, let's flash back for a moment. What is the formula for speed? Wow, you really trailed off on that one.
Distance over time?
There we go. I heard that. Did you hear her?
Sort of.
All right, so speed is distance over time. So if I'm producing a wave, again, let's go back to that. I assume when I'm doing this, you can picture what I'm doing. I'm hoping for some not battle ropes.
Oh, yeah.
Okay. Anyone no clue about what I'm doing? When I'm doing this? Was it your?
The rope.
Yeah, the ropes.
Yeah.
Okay. I was seeing if anyone was just had no idea what I'm doing. This is part of my acting improv mime class. All right. So if I'm producing a wave up and by moving my arm up and down, the time it takes for me to go up, down, and back to where I started is the period. How far it moves in that time is the period is the wavelength. So this would just be the wavelength divided by the period. Now I know that, so that's just wavelength times 1 over the period. I know 1 over the period is just the frequency, so this is wavelength times the frequency. So we have an equation that will pop up more than once, that for a wave, the speed of the wave is equal to frequency times wavelength. Or if you're feeling saucy, wavelength times frequency. Now why this equation right here, not only does it show up again and again, but it also, if you're looking at some other sources will not use F for frequency. They have this crazy notion that not everyone speaks English, and so why should anything be based on English words? Instead, a lot of things are based upon Latin words because everyone speaks Latin. Now, if you get into graduate work in physics or even upper level classes, the symbol they use for frequency is the Greek letter nu. That's how you spell it, and that's the symbol for it. Sometimes. So this equation will look like V is equal to nu lambda. However, some fonts make the V look like this and make the nu look like that. One of the reasons I don't use the letter nu. But if you run into some source that is using nu for frequency, look for this equation, because that will tell you how they're differentiating V and nu. This is going to be the frequency here. Now, quite possibly, and I'm hoping this is the last time we ever bring up the nu, but I just wanted to bring it up in case you run across it. Not to be squirrely. Now, what do waves look like? Yeah, battle ropes. Yeah, I think you can picture that. Or on a much smaller scale. There we go. There's a wave you can send back and forth awkwardly. So some waves will just physically look like that. You're standing at the side, you look at it, you go, okay, that looks like a wave. But other things like sound waves, there are sound waves, but I can't look at sound and go, how's this showing up in sound? Well, in sound, it's not a physical I'm looking at a profile, it's how close the molecules are together. So, the peak here would be a place where the air molecules are much closer to each other, and then you've got some ambient, how close they are together, and then where they're much farther apart, and then they start getting closer, and then get really close together, and then they start spreading out, and then they get closer together again. These points right here are known as compression, and the points where they are much farther apart than normal, rarefaction. And as the compression hits your eardrum, it pushes your eardrum in, rarefaction will suck your eardrum out, and then back and forth, and it's kind of like a Morse code, except your brain translates it into sounds you are more familiar with, hopefully into words. And so this top representative, this is how I would represent this. If I'm talking about sound waves, I'm not gonna draw it with a whole bunch of dots because that's a pain. This is the way I would represent it, where this would be high pressure or a high density, and this would be low pressure or low density. And then the middle is whatever the normal air pressure is around here. We have some microphones that hook to the LabQuests, and what they're measuring actually is air pressure. One other way that I would represent this is sort of an overhead point of view. Think of a still lake. You throw a rock into it, it goes plunk, and then you get this ripple going out. Where that ripple is, you would see a line, and then where the next ripple is, if I threw another rock into the exact same spot, I'd get a second ripple. And so you would tend to see those as potentially concentric circles or something along those lines, where these are the peaks, the trough would be in the middle. There is one application where we would be doing this, so that's one reason I bring it up now. We will come back to it. The other bit of vocabulary is longitudinal waves versus transverse waves. And I know I promised that we'd be doing a wave, so let's do it. What we're about to demonstrate here is known as a transverse wave. So it's something to keep in mind. We're gonna start over on this side and we're gonna move that way. So I guess everyone can see you, Caroline. So what's gonna happen is you're just gonna go up and down, and then when you do it, they'll all do it, and then they'll do it like in a stadium. So begin when ready. Nope. All right, let's try that again. We're gonna stand up on this one. Just put the chair back so that you can stand up. Let's do this right.
When it goes here, are we going back up here?
No, I was picturing sweeping it that way.
Like,
All right, so when you're ready. Okay, not the best I've seen, but that, notice your hands. I was originally picturing you'd be seated and then you would stand up and do